Okay, I'm assuming all of you all have basic knowledge of graph theory. So a cycle is something that looks like this thing. It's basically a sequence of vertices that are all connected to each other. Okay, so cycles have many properties. They're very useful to consider. So the first thing so there are two types of cycles that are nice: Hamiltonian and Eulerian. Hamiltonian passes through each vertex exactly once. And Eulerian passes through each edge exactly once. And now the main thing about Eulerian graphs is that they have a very nice property, which is that they exist if and only if each vertex has an even degree. So I paste the problem. So this is your first problem. Think about it for a bit and then tell me. Do people have ideas?
I'm not sure if this is correct. I mean, K5 is clearly not an Eulerian cycle.
These cycles can pass through the same vertex twice.
What? Isn't like that not possible in a cycle?
This is a circuit, Eulerian circuit.
But you written cycle, Guru.
Arey bhai, it's fine. It doesn't matter much. Why is this pen not working? If at any point you don't understand my handwriting, please tell.
But wait, like a cycle cannot by definition pass through the same vertex, right?
Yeah, so
So
bhai,
how can circuit be a cycle? Like you wrote there, circuit is
a
a cycle.
circuit.
It's not a cycle.
Arey bhai, do you understand what I'm trying to say?
Like, okay, but like,
This I mean adjacent.
yes, sure.
Okay, is this fine now?
Yes. Okay, so the one direction is like easy because like if like there is a if a there is a Eulerlian circuit, then each vertex has to have an even degree because like
Yeah.
there are two adjacent vertices.
Even someone has pointed this out on chat. Nice.
So we are done with one direction, right?
Yes.
It's even that, right?
Yeah, so what they were saying is if an Eulerian circuit exists, then every single time the cycle passes through a vertex, it contributes 2 to the degree. Because if this is the circuit, then every single point you get 2 from the degree where it enters. Here we have 2 plus 2. And a bunch of 2's is all obviously even. Is this fine with everyone?
Yes.
Okay, how do we show the other direction? Arav Mishra, this is okay, but it's not exactly correct because if we repeat this procedure, we could come back to a vertex on the path, not the starting point. It's not forced that we return eventually to the starting point. Like we could get something like we go this, and then we come all the way around here, and it's not exactly a cycle.
I mean, we can just consider the path point where we came back as a cycle, no? As a
Yeah.
starting point of the cycle. Like
Okay.
that is the cycle.
Yeah,
Yeah.
cycle, but doesn't pass through every edge. These edges are still left out now.
Okay, right. You need every edge.
Yeah. Okay, Paras, you're saying induction. How do you propose to do that? Paras, are you there? Okay.
Wait, can induction even work? Like deleting an edge or something. I don't think it works.
Normal induction doesn't work. Maybe you could do something different than normal induction.
We could do something extremal.
Like what?
We could do something extremal, like consider the maximum like cycle, which could pass through maximum number of edges.
Yes. Okay,
Then
so you have a cycle that passes through the maximum number of edges.
yes,
It's a circuit, so let's say it has some intersection.
yes, sir. So there are like some edges left out.
Yes.
And like since this is an Eulerian circuit, so it would have even edges. Like the number of edges in this circuit would be even.
Mm, not necessarily.
No, no, no. The circuit that we have drawn, like that would have even edges. Number of edges is even, right?
Even number of
Like,
edges.
yes. Like
Why?
in that circuit, because an Eulerian circuit always has even number of edges.
No, not necessarily.
What? Didn't we just prove that right now?
Like,
Like any circuit has even number of edges, right? We just did that right now.
no. Each vertex has even degree.
But you can have a triangle in that case.
Yeah.
Only
A
few.
triangle.
Yeah, I meant each vertex has even degree.
Okay, yes. Each vertex is even degree.
So in the original graph also each vertex has even degree. So if you consider the degree of the vertices which are like not in the circuit, so that must also be even. Like number of vertices adjacent to a vertex not in the circuit. That should also be even.
Yes.
So like consider some edge which is not there.
Okay.
Uh so let's say that edge is V1, V2, where V1 is in the circuit.
Okay. Okay. And such an edge exists because the graph is connected.
Yes.
Okay.
And now consider like since it has even number of degree, so there is even degree inside the circuit and there is even degree total. So outside the circuit also there must be even degree. So like you can if there
Yes.
exists a V2, there should exist another V3 as well.
Okay.
Now you can make this circuit mm,
You're on the right track. A good track.
mm, okay. Okay, V2 would also have an even degree, right? Like V2.
Okay, Arav Mishra, you're saying the graph has at least n edges. We've not yet proven that a graph with at least n edges has a cycle. We're going to prove that a bit later. Oh, so someone mentioned induction. Try thinking of an induction way to approach it.
Okay.
Either way, to complete this tour, the way you did it with V1, that it must have an even degree.
Yes.
That's why you also get V3 out of it.
Hmm.
You could do the same thing with V2 and V3
Okay.
and just continue doing it. And at some point, you must go back to a particular vertex which was already in your circuit.
Repeat.
Or,
Wait, repeat what you said. I didn't quite catch you.
and so what I'm saying is, you started with V1,
Yeah.
and since you said that the graph is connected and all of the edges are not used in the circuit, you must find some other vertex V2 from
Yeah.
some vertex V1 in the cycle you've taken,
Hmm.
right? And since V1 must have an even degree, you can also find a V3.
Yes.
Similarly, do that with V2 and V3.
Okay.
Since V2 also must have an even degree, it must go. And eventually, and now let's say the path that you're taking, you have extended the number of vertices in the path. Eventually, you must come back to a particular vertex that you have considered because the graph is finite.
Okay.
And then you have a circuit.
No, but like the graph.
Like, how's there a contradiction? Like, we have a max circuit and we have a sub circuit over here that doesn't quite give us anything.
Yeah, but now you have a longer cycle that passes through more edges. That's a contradiction.
Okay, so you're saying we do something like we traverse the graph like this.
Yeah, yeah,
We come here, we go in this circuit.
yeah,
Okay. That is the correct solution.
yeah.
Okay, so what Akshar is saying, say we have a max circuit. This is our circuit. And say this doesn't contain everything. So there's something outside here. Because it's connected, there has to be some vertex on the circuit, V1, that is connected to something outside the circuit, say V2. Okay. Our assumption is that everything has even degree. So V1 already has even degree in the circuit. So V1 has to have at least another neighbor that's not in the circuit. Say V3. And what we can do is we can say the same argument for V3. V3 has an even degree. V3 is not in the circuit and is connected to V1. So it has to be connected to something else. And then we can get another cycle. And now the reason the cycle gives us a contradiction is because what we can do is we can traverse this part of the graph, go around the cycle, and then continue in the circuit, which contradicts maximality.
But like V2 could be in the circuit. And what if V1, V2 is not in the circuit, but V2 is in the circuit? So that's like,
No, but the edge is not in the circuit. That's what matters.
yeah, true then.
Yes. Then we still get another part of the circuit which we can traverse. We're not assuming that there are more vertices not in the circuit. We're assuming that the edges aren't there.
No, like the vertices could be in the circuit, right?
Yeah. V2, V3 can be in the circuit. Like V1 could be appearing somewhere else here too. The point is that these edges are not in the circuit. Since by
Wow.
definition,
Sure,
it is every edge.
sure.
Is
Okay,
it fine?
yes, works.
Okay. Everyone clear about this?
Though, how do you induct?
Okay, induction is basically the same thing. So what we do is every vertex has degree 2 or more now, because every vertex has even degree we are assuming, and it's
Yes,
connected. So no vertex can have degree 0.
yes, so there exists a cycle.
Yes.
So,
This is just because we can keep on going and going
yeah,
until we get a cycle. Okay.
yes, true. Then,
Now our assumption is, so what we do is we delete the cycle. Okay.
okay,
Now we are left with some subgraphs which were
yes,
connected to
which is
this.
reconnected.
Yeah. Now in each of them by induction, we have an Eulerian circuit.
Okay, sure, inducting on the number of edges.
Yes.
Sure, it has.
So
Okay,
then what we do
predicate
is,
our cycle.
yeah. So
Okay,
we do to find the Eulerian circuit once we put it back together is go around like this. The circuit here, we traverse it and go to the next one. So there's like a bunch of islands and we're taking a tour. Island 1, we tour the whole place and then we go to the next island and so on.
okay, makes sense.
Okay.
No, wait, but like for induction to work, we need that in the deleted like the graph after which we get after deleting should have like all degrees even.
Yes, that's because we're deleting a bunch of, because we're removing a degree of 2 from these edges.
Okay.
Like we're not deleting the graph, we're deleting the edges. That's the key point.
Yes, okay, sure.
Is this fine?
Yes, it's fine.
Okay. Everyone clear about this?
But like, what about the base case?
That is easy to check. You can try it yourself.
Okay, sure.
Okay, have you all seen this before? It's a pretty common result, so
Yes.
I'll give a buffer. Okay. Okay, so this is your buffer if you've seen the previous result before. How many of y'all have seen this result before?
I remember seeing it, but I have not I forgot the proof.
Okay, a few people have seen this before. Okay, so it'll be better if we try this buffer instead. I'll put this on the P set. I'll let you all think about this for about 10 minutes. Does anyone have any ideas?
We could create a bipartite graph or something.
How do you get a bipartite graph?
Um, not sure.
Okay, start by trying out few small cases, even if you don't like to do it. So I'll draw a small grid here. Note it says n is an odd integer.
Okay, so maybe we can do chessboard coloring.
What do you do?
Chessboard coloring, like
Chessboard coloring, okay.
and then you can see that a move consists of shifting an empty square to like uh, a square of the same color.
Hmm.
And like since the bottom left and the top right square would be of the same color if they are would be of different colors if they are even. So we have proven that we can't do it for even.
Dude, for even you cannot even have domino tiling because then the number.
Right.
Exactly.
Okay. So
I guess so. If we're like moving the gaps, then we can sort of look at the path which the gaps follows. That's along the dominoes.
Repeat your idea.
So when we slide a block into the gap, then the
Yeah.
gap sort of moves along the domino.
Yes.
So maybe we can try to find paths like that. Work with it somehow.
Okay. Okay, so where is the gap always? Like, what can you tell about the cell the gap is at?
it's on the same color. Like it would be either like two right or two above, two left.
Yes. And so it's always, both coordinates are always odd.
Yeah.
So I'll just mark those cells. So these are the cells you want to look at. Okay.
Yes.
Okay, so say that no matter how we push the tiles, we never reach the very corner. Okay. What does this mean?
Like this means there is no path that could lead us from the bottom left to top right.
That
That
means that the two neighboring odd spots that you have, they also can't be reached, right? Something like that. Like the top right corner has one domino. So
Hmm.
along that domino, the next uh, cell, that also can't be reached. Because if that's reached, then we can move this one and reach our
Okay.
horizon thing. So we can continue doing this and originally maybe come to something that is obviously achievable.
Okay, that's the correct intuition, but that's not very easy to formalize.
Ah, okay.
Like we can connect two dots by a line if we could reach
Yeah.
from one dot to the other to a move. So like we can observe that each dot would be connected to exactly one.
Okay, what do you mean can be reached by something else?
Like by reached by a move.
Okay. And if we can draw a line between two dots, then what will this line look like?
Like the line you have drawn is like
Yes.
that.
So if we drawn across few dominoes
Yes.
like this, okay?
Yeah.
Now
So
think
like
about my original question. What does it mean if we can't reach the very end?
there is no path from the top left, bottom right, bottom left to the top right.
Yes, there's no path. Oh, so we'll clearly define what our edge is. Our edge is this clear?
Yeah, that's what
So
this
basically the
means.
points and the domino, okay, they're right.
Now just prove there's a path.
Yes.
So one thing I got is that if you have n such points, then there are n minus one, like n minus one dominoes, which will give an edge. So
If n such points, n minus one dominoes are given edge. Why?
every one of them other than the gap has exactly one domino on it.
Okay, yes.
Yeah, so we need to prove that it's a tree. Or I mean, I'm not sure if that's true, but like we need to show these two are connected.
Hmm. Okay, so basically what we want to do is if there's a path from here to here, we'll slide it across the path now. Which is
Yes.
fine to everyone. So what happens if there is no path? So we keep on sliding across whatever is available. Then what do we get? Think about what the topic of this class is.
You will get a cycle, right?
Yes. Now the main thing is you want to show that no cycle can exist.
Yes.
So you just say some cycle exists. Let me draw out something.
Like if there is a cycle, then each vertex in that cycle would have an even like degree.
What's wrong about that?
There's something wrong, sure.
You have to tell me
Okay,
what's
wait. The graph is connected, right?
Yeah, it has to be connected.
not necessarily. You want to prove that it's connected.
Like if we have proven that it's connected, then you're like done because then it will be a tree.
Like if it's connected, then there's obviously a path from the starting to the end.
Oh,
Wait, but isn't it obviously connected? Because
Why?
I mean, see, you don't care about the other vertices, right? So you only care about the top right cell. So you don't care if all the other ones are not in the graph. If some of them are not in the graph. So if you assume the contrary, that the top right is not in the graph,
Yeah.
then you can like create a path from there, in the sense that
Yes. But the point is, what if it comes back to itself?
what if you have a cycle? That's what, right?
Yes. What if we have a cycle?
Okay, yeah.
Like the only way this problem can be false is if there is a cycle.
Okay, so we'll show that.
Yeah. So say there's a contradiction. So say there is a cycle which looks something like this. What is the contradiction that we get?
it must be related to dominoes placing, like
What do
something.
you think?
The contradiction must be related to like placing of dominoes or something.
Mm, what do you mean?
Like if you have a cycle, then you do have some constraints on placing of dominoes, and probably you cannot place dominoes according to those constraints.
Or what are the constraints?
That's what like we need to
Yeah,
find.
that's what I'm trying to ask you. So draw a few examples of cycles and see what goes wrong. Like, like it's possible for there to be a cycle now. Like I just drew a cycle.
Yes, it's possible to.
Yeah, but then what's the contradiction?
The contradiction is you can't then place dominoes at all.
Yes, you can't place dominoes inside here
Yes,
because they're an odd number.
yes,
Because because whatever is in this place, it has to be tiled by dominoes now.
yep,
And we're assuming the hole is not in this place because the hole is at the very corner.
yep.
So you want to show that if we have a cycle, the internal region
Yeah, I think
is
whatever rectangle you're gonna form using this, it has to have odd by odd sides. Something like that. In the sense that here we have a particular rectangle formed, right? Or whatever space we have.
okay, cycles can be a bit funky, like they can be something like this. They can be funky like this or something.
Yeah, that's okay.
They don't have to be a rectangle. Okay, but it's not very hard. Like the idea is we can just induct.
Mm. Yeah.
I'll leave that as an exercise. Is this clear to everyone? Is this fine?
Yep.
Hello, people.
Yes.
Okay, nice.
Yes, yes.
Okay, I'll put the next problem now. Okay, for those of y'all who like linear algebra, we're doing this problem without linear algebra. So just remember that. Okay, for this problem, it'll be
Isn't it like same as the
yeah.
problem, like same as the number of cycle is a power of 2?
Why is number of cycles a power of 2?
Because like if you choose something in such a way that it has to be a cycle, like there is exactly one road leaving and one road coming.
Wait, I didn't get it.
Can you show the problem on me?
Okay. Okay, do you all know what bipartite graphs are?
Yes.
Yeah.
Okay. You will want to keep this in mind about this.
Oh, I think any such way, like if you create a directed graph, then any such way must be a union of cycles.
What do you mean it's a union of cycles?
Like, it's just various cycles put together. Like, it's a graph whose connected components are cycles.
Is this necessarily true?
Yes, like it is necessarily.
No, I can construct a counterexample.
No, but like each city has should have like one road leaving and one road entering.
2 rows entering and 2 rows exiting.
No, exactly one road leaving it and exactly one road entering it, right? Like the chosen graph, I mean.
Yeah, the chosen graph.
And the chosen graph is a union of cycles.
Yes.
Right. Chosen graph is the union of cycles. And so let's say there are k cycles. You just have to do the k ways of choosing cycles. Or something like that.
So you'll want to think about what does the graph look like?
Yeah, the chosen graph looks like a union of cycles.
Yes.
Is like, am I correct?
Yeah, that's not that hard.
Right, the chosen graph is a union of cycles. And conversely, a union of cycles satisfies the condition of the chosen graph.
Yes, directed cycles.
So all the number of ways of choosing are exactly number of ways of choosing a subgraph, which is a union of cycles.
Yes.
So let's say the graph contains k cycles, then like there are 2 to the k ways of choosing those cycles.
Why are the 2 to the k ways of choosing the cycles?
Okay, yes, cycles could be. No, like if there are k objects, then there are 2 to the k ways of choosing them.
You're choosing a subset of them. We're not choosing a subset. We're deleting edges and we're being left with cycles.
Yeah, I mean like cycles could not be disjoint. Like if all the cycles were disjoint, then we.
Wait, so you want to think about what is the structure of such graphs? Like what type of properties are in such graphs?
Is this correct? Like, there are k cycles suppose in the graph. We can like prove that there are at least two cycles in the original graph. Then we just need to select a unit of cycles. So there would be two to the k ways of doing that.
No, I don't think that's fine. That's right.
Okay.
So can you do something like this? You can start with a particular vertex
Okay.
and choose one of the two edges that go out from it. So
Yeah.
choose one and you end up at one vertex. Do that again. Continue to do that, basically.
Okay.
And you must end up in a cycle.
Yes.
Now we want this to be Eulerian. Can this be Eulerian?
Why do you want this to be Eulerian?
Because then the
The graph is not
remaining.
necessarily connected.
Oh, is it not connected? Okay, there's nothing mentioned.
But like you can assume it's connected and then prove it on each connected component.
Yeah,
Okay.
that's okay.
So you have some connected component.
Mhm.
We could prove that like the final graph is unit of cycles like the graph we chose, right?
What
Hello. Hello. Hello.
Yeah. Yeah, I'm not getting the idea.
No, no. Let like the final graph. Let's say we first create a directed graph of the entire nation of Onevena.
Yeah.
Then, like the graph we chose from the Onevena in the way that is described in the problem. Let's call that graph the chosen graph.
Okay.
Now I am saying that chosen graph should be a union of cycles, a union of disjoint cycles in particular.
Yes.
Is this like true, right?
Yes, yes. This we agreed on before.
Yeah, so we just have to find the number of ways of choosing a union of disjoint cycles from the original graph.
Okay.
So like we can observe that there are at least two cycles in the original graph, right?
Why?
Because
Okay, yes, yes.
we can start like we can take a vertex and start with one road leaving it, then start with the other road leaving it, and we'll get two cycles. Right?
Yes, yes, I got it. Okay. Then
Then I'm not sure.
If you can partition the entire graph into cycles, then you're done, right?
but that is like not true. We cannot partition.
No, we want to delete edges so it's a bunch of cycles. But like, how do we do this? Okay, so what you want to think about is, say we delete some edge like this. Okay. So we delete it. Now, how does the remaining stuff that we are forced to delete look like?
What?
Now you must also delete an edge that goes out from the other vertex, right?
So say this is V1, V2. What do we have?
We have to delete one vertex that goes out from V2.
Okay. But it's a bit ambiguous, like which one?
Someone, something.
What's better is we have something that's incoming into V2 now, which we know we can't delete.
Okay, yeah.
Right. So say this is V3. Now V3 has something coming out of it.
Okay, so we are forced to
Okay,
delete the
so
other.
you're putting these edges into two sets, right?
Okay, we can induct probably.
How?
Like, first, you like cross an arbitrary vertex, like edge from V1. So there are two ways of doing that, and corresponding to two ways, like we could perhaps prove that the remaining thing has to do the like 2 to the power something ways by induction.
What you're saying is very imprecise. You have to make it more precise. But I see where you're going a bit. Hey, there's something in the chat. Let me see. We can construct a simple undirected bipartite graph such that the subgraphs correspond to perfect matchings of the graph. Okay, I wonder how you thought of this idea. If the graph has n cycles and the number of perfect matching is 2 to the n, okay, that is correct. But I wonder how you thought of it. Okay, this is the correct idea. Arav Mishra. Would you like to share your motivation? Okay, Sanskar, continue thinking about this idea. Like what Arif put in the chat is a different idea of different way of doing this. Like I know at least 5-10 solutions to this problem. Continue thinking about this one.
Okay.
Okay, so with this process, if you continue this process, then you're going to get an alternating sequence of edges that you can delete, right? You have to do it basically if you delete the first
Yeah.
one.
So what does this alternating sequence of edges look like? It's a cycle now.
Yeah.
So we have a cycle. Now how do the edges of the cycle look like? The edges have opposite orientations.
Yeah, yeah.
And now what we know is that we have to alternately delete edges from
Yes,
this.
the cycle has to be even.
Yes, it's even cycle. Even cycle, opposite edges.
So are you saying we partition this into two sets?
Yes. So the thing is, what we do is we break this original graph G into these so-called anti-cycles. Okay. Anti-cycles are basically the even cycles with opposite edges. Now each anticycles, we can delete the edges in one of two ways. Because you have to do it alternatingly now. So we can do it like this, as I drew in the diagram, or a tiny bit differently, like this. Brown or red.
No, but like anticycles need not be disjoint, right?
Yeah, they need not be destroyed. The thing is, say we consider a vertex in the anticycle. Okay. Both of its incoming edges are in this anticycle since it has exactly two incoming edges.
Yes.
So 1, 2. We have to delete one of these. Say it's the brown one.
Yeah.
Now, the moment we delete the brown one, we are forced to delete these two brown edges.
Yeah, like if you delete one edge, then you are forced to delete.
Yes.
Like you have only one
And you
possible.
have to delete something in the anticycle because of this.
Yeah. So there are like exactly two ways of
Yeah.
deleting
Each
the
anticycle has two ways of being deleted.
Yeah.
So that's the main thing. So like, can we partition the graph into anticycles? If we can, then we're done. Because each anticycle can be the
You
edges
mean
can be
disjoint
deleted.
anticycles or what?
Not disjoint. The edges are disjointed anticycles. The vertices
Yeah, sure.
need not be. And the decision of one anticycle is independent from the other.
Yeah.
So why is it necessary to tile the graph with anticycles? This is the simplest part. Induct Nina.
Yep. So we can like first prove that each vertex is a part of an anticycle.
Yes.
So we could like create that by like simple process.
Yeah. You get an anticycle, delete the edges, and continue.
Yeah, but like we have to first prove that all vertices are a part of anticycle.
Yeah, that's simple. This
Yeah.
like
Uh,
edge has an in degree of 2 now. So you
yeah.
have the edge
Yes.
has a degree of 2. This must have some out degree, and then you just keep on going.
Yeah.
And then at no point can it be you come back to something over here. Why is that?
What? Can you repeat?
I'm saying we over here, I said we repeat now, but then while repeating, what happens if we come back to something in the cycle instead of all the way back around?
The vertex is then like it's like not an anticycle.
No, it is an anti-cycle. But then we don't
Like
get it as an anti-cycle necessarily containing this. Like, what's the contradiction that comes around here? Think about where it comes back now. So it comes back somewhere over here. Okay.
yeah.
So the three, ed three edges of the same vertex in the anticycle. It's just like
Yeah, that's the contradiction. Okay, so does this solution make sense? What we did is we broke it down into these anti-cycles. Each have two ways of edges being deleted. So we're done.
wait,
Is this
okay. But why do the anticycles have to be disjoint?
they're not disjoint. The edges of the anti-cycle are disjoint.
Yeah. But how have we shown that the edges are disjoint?
Because the thing is, this edge, say, so we have this vertex, it has a degree of 2.
Hmm.
So both of it's in both edges pointing towards it are in its anticycle.
Yeah.
These two edges can't be in any other anticycle. Do you get why?
Yeah, I get it. Yeah, because you end up in the same thing, right? If we assume that they're part of two anticycles, you'll just have a contradiction.
Yes.
Yeah.
Okay, so now the other solution which involves bipartite graphs, what we do is 1 minute, I'll be back in a moment. Okay, so the contradiction so what we do is we construct a graph, a bipartite graph, one vertex at A, one vertex at B. Okay. The vertices of this are the cities of Onvania. Okay. So each of these dots, cities of Onvania. The vertices of B also, cities of Onvania. Is this graph clear to you? What we're doing here?
Yes.
We're creating a graph on this graph, and the way we make. Okay, does anyone have a guess on how we're drawing the edges? Okay, so what we do is, if in G, the original graph of one vania, A points to B, we draw an edge between A and B over here. Okay. Now the thing is, this do you all get why this graph is properly defined?
Yes.
That this is a proper definition. Okay.
Because like there cannot exist two edge between A and B.
Yes. Now, what the original condition states is that every vertex in this graph has a degree exactly 2. Do you all see why this is the case?
Yes.
Yeah.
And out degree of exactly 2. And in degree. Right.
Yeah, because every vertex in B has a degree 2, since
Yeah.
and every vertex in A has a degree 2, because the neighbors of A represent the things that in the original graph of G it points outwards to, which we know there are 2 of. And B says the things that points inwards to it. Okay, so 2 and 2. Now every vertex has degree 2. What does a graph with every vertex of degree 2 look like?
The every vertex would have degree 4 in the bipartite graph, right?
Why?
Like there are two edges to which it points and two edges which point towards it.
No, these two are separate copies of the graph itself. Are you getting what I mean?
Yeah, these are separate copies. So like suppose V1 is there. So suppose like it is pointing to V2 and V3 in the original graph. So
Yeah.
we would have V1, V2, V1, V2 and V1, V3 in this graph. And suppose like V5 and V6 point towards V1.
Yeah.
So we would have V5, V1 and V6, V1 also in this graph, right?
Okay, I don't think you fully got it. What we're doing is we're making 2 copies of it. So this
Wait, are you creating only edges from A to B or you also doing from B to A? Like
wait, let me clarify. So we have our graph G. Okay. Its vertices are V1, V2, so on till Vn. Okay. So we
yeah.
take edges A1, A2, vertices A1, A2 till An, and vertices B1, B2 till Bn. Now if Vi points to Vj in our original graph, we draw an edge between Ai and Vj.
Yeah, that's what I'm asking. Now you are drawing from edges from set A to set B, not set B to set A.
Yes.
Yeah, that is what I was asking.
So Vi points to 2 things, Vj and Vk.
Yeah, then it has two edges.
Yeah. So this points to 2 things. Vj is pointed to by 2 things. So, okay, that's clear. Now every vertex has degree 2. what can we say about a graph in which every vertex is degree 2?
There is a cycle.
We can say something stronger than there is a cycle.
It is a union of cycles.
Yes. Union of disjoint cycles. Okay. Now say we have some cycle in our graph. A1 points to B1, A2, B2, A3, B3, and then back to A1. Okay.
And since the graph is bipartite, each cycle has to be even.
Has to be what? Even, yeah. Even cycle. Say we have this even cycle. What can we say about this cycle? What does it look like in G? Say, okay, so we have this edge A1 to B1 in G now. Okay, wait, no.
We can't have A1 to B1, bro.
Okay, wait. I've messed up the notations a bit. Say it's X1, Y1.
Yeah.
Well, let's just say X, Y. Okay, wait. My bad.
Just mark it ABCD, yeah, bro.
So this looks like an anti-cycle, right?
Yes, that's the point. X, Y,
Okay, so you're done because
TV.
you can partition it into anti-cycles.
Okay, don't think about it as anti-cycles. Think about this as a new solution.
What?
Okay, fine. Yes, this is basically why we can partition it into anti-cycles.
Yeah.
So we're done. Are you all convinced?
Yes, yes.
Okay, so do you all want to do? Okay, so I'll put some more nice problems in the P set. I'll also put some theorems in the P set like that you all should prove. Do you all want to do another problem before we go?
Sure.
Okay. Arif, I'll send the P set later. It will be shared on the OMC server. Okay, let's do a problem which I also haven't done. Okay, actually, no, this is a nice problem we also do, which I have done. Have any of you all seen this before? Okay, I think the meeting will end in 3 minutes because of the scheduled meeting time.
I don't think that happens.
Oh, okay. Because it had like a red warning type thing.
Maybe
Okay,
it
then
does
I think
happen. We will restart it. It happens.
Okay, in fact, I'll put this on the P set because I'll have to leave in 5 minutes anyways. If we don't do this in the next 5 minutes, I'll put it on the P set.
Okay.
Okay, so it feels like with every edge that we add, we're either adding a constraint or like so we're either adding a constraint of the form that like you're completing the coloring for that connected component, or we're not really doing anything. So and ideally you would want to add a constraint in your turn because like adding if you're completing an event cycle, then that's not really doing anything. Like you might as well have done it at the end, or someone else could have done it at the end.
Well, I was talking on mute. I'm saying this is a good intuition, but what exactly do you mean by constraint? Like, what are you constraining?
No, so like for each of the connected components, you have a coloring which is already fixed in two colors. And like when you connect two components, it just shows you how to align the two components. So you might have to switch the colorings for one of the connected components.
Oh, you say thinking of it as a bipartite graph.
Yes.
Okay. So the moment someone loses, what does the graph look like before that? Like the moment someone is forced to lose.
It should be bipartite.
Yes, a complete bipartite graph. Yes, that's correct, Arav. So what Arav is saying is, say it's odd. So one of the two parts would be even. Okay. So the total number of edges is even. Okay. So the person who places the edge that makes it lose, which is something like this, that person is the person who plays the odd turns, or the first player. Now when n is even, you'll have to take a bit more care, since like it's possible that the final thing is odd, odd, or even. So someone will have, so both players will have to be smart about what exactly they're doing. So the thing is, the players want to force how the bipartite graph looks like. Oh, if for 4 divides n, we can. But ask, why do we get the second guy to win?
If we divide the total number of vertices into four parts, Jacob will like just copy what he's doing. Like the second guy will just copy what the first guy doing and stuff.
Copy in what sense?
Or like, should I write and send you?
How are you copying the other person? Okay, no worries. Okay, just try some base cases. Try n is equal to 6. What can both the players do? Okay, I think I see something we can do with your idea of copying. Basically, what we do is say it's A, B, C, D, and someone plays something like A to B, then then the second player puts C to D. If they put A to A, then they put C to C, so on. Is that what you're trying to say?
Yeah.
Yes, that works. Basically, you have groups x1, x2, x3, x4, each with 1 to k, 1 to k, 1 to k, 1 to k. And if we draw an edge between, say, group A, say, for example, say 1i and 2i, we add like 2 mod 4 to become 3i and 4i. Basically, statically shifting it by 2.
Yeah.
Okay, so now what if n is 2 mod 4?
Yeah, I am thinking that.
Wait, so in this case, what happens if there's an edge from I to, if there's an edge from x to x to I plus x,
From what to
like
what?
an edge from A to C.
Then like similarly B to D, I think.
Yeah, you add it to B to D.
Okay.
Okay, so now we're left with the case n is 2 mod 4. Okay, I have to leave now. I'll leave this as a problem in the P set now. Shreya, can I just end the meeting or
Okay, I'll stop the recording. Wait, no, I can't. Stop the recording.
wait, I can stop the recording, yeah.